This section will take a look at surface integrals. And we're starting to wind down the course itself, but we've integrated over this course along a line, region in the plane, along a solid region, along a curve in space. So in this section, we're going to take a look at how to integrate on a surface. And the example that I gave up here in the PowerPoint was temperature distribution on a surface. If you think of adding up all those little temperatures together, you might be able to find the average temperature on that surface. Now, there's two different versions of this, one in which the surface is written in parametric form, the other where the surface is defined explicitly. Well, at some point in this course, we have to make a decision to say just how much we can cram into one calculus course. So we're going to focus on the explicitly defined cases. So if you look through your textbook and you find references to things that are implicitly defined, if you want to read through them, that's certainly fine. But we're going to concentrate here on explicitly defined cases. So let's take a look at the formula that we're going to use for this. Evaluation of surface integrals on explicitly defined surfaces. And you notice that for explicitly defined surfaces, we're defining z as explicitly a function of x and y. So z equals some g of x and y. The surface integral is given like this. It's a double integral integrated over the area of the function square root of partial z with respect to x squared, partial z with respect to y squared, plus 1. Now, if your f of x, y, z is 1, then really what you're doing is you're finding the surface area with a slightly different looking formula. Let's start with this case over here. I've got a plane, and I've got an ellipse on the bottom, right? So I'm looking for the roof over an ellipse. The roof over the ellipse is this blue region over here. All right, the plane is that blue region, 12 minus 4x minus 3y. It intersects the region x squared over 4 plus y squared equals 1. I'm going to integrate this over the area of the base in order to find the surface area of that region. So the first thing I might do is I might set up my double integral. Double integral, if we're finding the surface area, then our f of x, y, z is equal to 1. So 1 square root of, now, this is the function here that we need to take partial derivatives of. So we're going to take the partial derivative of that function with respect to x, which just gives me negative 4, and we'll square it. Then we'll take the partial derivative of that function with respect to y, so that gives me negative 3, and I square it, plus 1. Integrated over the area of the base. So this gives me, let's see, if I do a little quick math here, 16, 9, 1, so that gives me a 26. All right, so I'm looking at the double integral of the square root of 26 integrated over the area. Now, I could save myself a whole lot of time if I could only find the area of an ellipse. Now, was it 1, 2, 3 lessons ago that we had come up with the area for an ellipse as pi times a and b, where a and b are these numbers on the bottom. So the square root of 4 is 2. The square root of 1 is 1. The area of my ellipse is 2 pi. And so now I can actually finish this problem off. The area is 2 pi. Multiply it by the square root of 26, and I'm done. So if you ever have a roof that looks like this, and you want to find the area of that roof, now you know how to find the area of the roof. Good. Let's try another one. This says find the surface area of a paraboloid. Right? Paraboloid is one of these combination parabola ellipse things. It's got a little circle on the roof. There it is. Right? Z equals 2x squared plus 2y squared, and I want it true for z values between 0 and 8. So again, I can set this up in one of several different ways. Why don't I start by acknowledging that if I'm finding surface area, then f of x, y, z equals 1. I can also find the partial derivative of z with respect to x, partial derivative of z with respect to y, because I'm going to need that in my calculations. Well, the partial derivative of z with respect to x is 4x. Partial derivative of z with respect to y is 4y. Notice that I wasn't given any information about r, right? R is supposed to be that region that covers this thing. So what is the region? Well, here we're going to look at this information. The z values go from 0 to 8. So if z is equal to 2x squared plus 2y squared, and z also is equal to 8 at some point, then divide both sides by 2, and I get x squared plus y squared equals 4. So R is a circle with a radius of 2 centered at the origin. All right, so when I set up this double integral, it's going to look like this. I'm going to have a double integral of the square root of 4x squared plus 4y squared. So don't forget, when I square a 4x, I get a 16x squared. And then I get a 16y squared plus 1 integrated over some area. Now, perhaps this would be easier if I could turn this into cylindrical coordinates, because that 16x squared over here and 16y squared is going to be tough to find the antiderivative of simply. So let's convert this to cylindrical coordinates. What's the advantage of cylindrical coordinates? Well, for one thing, I know that x squared plus y squared equals r squared, so I can take the square root of 16x squared plus 16y squared and write it like that. And that will then let me write, here, I'll put this up at the top here, x squared plus y squared. I can now write this as the double integral of the square root of 16r squared plus 1. And then don't forget, when we're integrating in cylindrical coordinates, we have to integrate the function r dr d theta. And if I'm doing it that way, my inside limits of integration become the r. Well, we said that the base was a circle with a radius of 2. So the limits of integration for the r go from 0 to 2. And then how about the theta? Well, if I'm going to make a circle out of it, it's got to go all the way from 0 to 2 pi. All right, how do I integrate this? U substitution. So let's let u be what's underneath that radical, 16r squared plus 1, which makes my du 32r dr. Well, I only want a 1r dr. So as funny as this looks, I'm going to write 1/32 du equals r dr. All right, so what I'm focusing on right now are those inside limits of integration. The other thing that's going to be funny is I need new limits of integration. So u evaluated at 0 is going to give me 16 times 2 squared plus 1. 4 times 16 is 64 plus 1 is 65. Nope, that was the upper limit of integration. Oops. And then u of 0 is just going to be 1. So now this gives me the integral from 1 to 65 of 1/32 square root of u du. All right, nobody promised that this was going to be the easiest or cutest looking thing, but I'll get 1/32 of u to the 3 halves times 2/3, which will give me 1/48 65 to the 3 halves minus 1/48 times 1. Now, I've got to take this and integrate it from 0 to 2 pi. But you realize that that part's the easy part, because once I have 1/48 of 65 to the 3 halves minus 1/48, if I integrate this from 0 to 2 pi with respect to theta, all I'm doing is multiplying that by 2 pi. So I get 2 pi times 65 to the 3 halves minus 1 all over 48. And if you want to simplify it any further, you can do that, right? You can write the 65 to the 3 halves as 65 square root of 65 if it makes you feel better, but that's what you do. So sometimes converting it to cylindrical coordinates makes it easier. All right, let's take a look at another example. Here I'm trying to evaluate a surface integral for a function that is not 1 anymore. Right now that function is given as x squared plus y squared, and the surface that I'm evaluating it over is a paraboloid with z values from 0 to 4. Where do we start? Well, we know what f of x, y, z is, right? F of x, y, z is given as x squared plus y squared. We should take some partial derivatives. The partial derivative of z with respect to x is 2x. The partial derivative of z with respect to y is 2y. Now, let's set up the first round of the integral. So we're going to take the double integral of f of xy, which is x squared plus y squared, and then the square root of the partial z with respect to x, which is 2x, square it. Partial with respect to y is 2y, square it. Add 1. We're integrating over area. Expand this out a little bit. Double integral x squared plus y squared. Square root of what? If I square the 2x, I'll get a 4x squared. If I square the 2y, I'll get a 4y squared. So when I add them together, I'm really adding 4 times x squared plus y squared plus 1. Integrated over some area. Do you see where this is heading? This would be good to turn into cylindrical coordinates. Question is, what do I use now for limits of integration? So I'm going to replace all of my x squared plus y squares with r squares. Okay, so this becomes a double integral of r squared square root of 4r squared plus 1. Now remember, when we turn this into cylindrical coordinates, it becomes the function r dr d theta. Well, the thetas I'm pretty confident are going to go from 0 to 2 pi. Question is, what are my limits of integration for r? I'll come back to the original problem, and it tells us that the z values go from 0 to 4. So quick calculation, if I put a 4 in for z, this is another circle with the radius of 2. So my r values range from 0 to 2. In this case, the setup is not bad. It's the integration that becomes the issue. Because if you look at this inside piece over here, remember you integrate r dr d theta. So this r over here gets multiplied by that r squared over there. So now you're looking at the integral of r cubed square root of 4r squared plus 1 dr. We're used to having the r with the bigger power on the inside and the smaller power on the outside, in which case we just let the u be the inside function and the outside function becomes my dr. But that's not what we have in this case. So what do? Well, there's two ways that you can do this. If you have sort of a daring personality, you could look at what's under that radical and go, I see a tangent in there somewhere. I'm going to do it by trig substitution. And you could take that 4r squared plus 1 and say let 2r be the tan of theta. So r is 1/2 tan theta. And then work your way through some trig substitution. Okay? Does it work? Yes, because I did the whole thing by trig substitution until I went, there's actually an easier way to do it than trig substitution. So I'm going to set it up. I don't know if I'm going to work all the way through it, but at least I want to set it up to show you how it works. What you would do is you would say, I want to take the integral of r cubed square root of 1 plus 4r squared, integrate it with respect to r, and then I'll still let that u be 1 plus 4r squared. When I derive that, my du will be 8r dr. And so 1/8 of du equals r dr. The other thing then what I'll do is I'll take this top line up here, and I'll solve for r squared. I'll say u minus 1 divided by 4 is equal to r squared. And then when I come over here and rewrite this, I'm going to rewrite this as the integral of r squared, square root of 1 plus 4r squared, times r dr. And so the r squared, I substitute with the u minus 1 over 4, right? That is the r squared. No need for a square on the outside. The middle piece just becomes the square root of u. And the RDR becomes a 1/8 du. And from here now, I can simplify a little bit, right? I'll get 1/8, the integral. If I multiply u to the 1/2 times u to the first, I'll end up with a u to the 3/2 minus u to the 1/2 all over 4. And then why not pull that 4 on the outside? So I come up with 1/32 integral of u to the 3/2 minus u to the 1/2. And then the only other thing I need to do is worry about the limits of integration. The original limits of integration went from 0 to 2. So the new limits of integration will go from 1. And then if I put a 2 in here, 2 squared is 4. 4 times 4 is 16, plus 1 is 17. All right. And then I'm going to let you carry that on from there. When you get done with that, then you would integrate with respect to theta, which really in this case just means multiplying your answer by 2 pi. But I at least wanted to show you how to set that up. And yeah, every once in a while you do come up with a funky integral when you do that. You can do it by trig substitution, or you can do it by this method where you try to get the u's and r's into some relationship that you could do a substitution. Now let's take a look at surface integrals for vector fields. The surfaces in this book are what we call orientable. They're two-sided. You can orientate them in different ways. If you walk along the surface at the start and end points, the normal vectors point in the same direction. Is that always true? No. So I put this little picture here of a Mobius strip. You know what a Mobius strip is? You take one piece of paper, you fold it so the top of one becomes the bottom of the other. If you try walking along the Mobius strip, at this point here, the normal vectors are pointing upward. As you walk along that dark gold sort of part of the strip, you're walking here, you're walking down this way, down. By the time you get back up here, now you're walking upside down. Good luck with that. But you notice that the normal vectors are now not pointing in the same direction. In this case, the problems we're doing, the normal vectors will all point in the same direction at the start points and at the end points. But there are surfaces like this Mobius strip where the normal vectors do not point in the same direction. But we're not going to quite worry about that here. Flux integrals. Most common types of surface integrals are flux integrals. They tell you things like flow of liquid across the surface. Are your normal vectors pointing towards the surface or away from the surface? So if you have an explicitly defined surface, and again, those are the ones we're focusing on in this section, you can find the flux across the surface by doing negative f times the partial derivative with respect to x minus g times partial with respect to y plus h integrated across some area. So how does that work? The negative partial f with respect to f zx g zy plus h, and you're going to integrate that over some area. All right, let me do an example and show you how this works. So I got a vector field f of x, y, z. Right? Pretty simple looking vector field. This one lives on the slanted face of a tetrahedron. Right? You know what a tetrahedron is? It's just a pyramid whose sides are all equilateral triangles. Tetra meaning four equilateral triangles. If you sat it down, it would look like, well, it would be a triangular pyramid. The surface is z equals 10 minus 2x minus 5y. We're talking about the first octant with the normal vectors pointing upward. So it seems like for my formula, I need a partial derivative with respect to x. So the partial derivative with respect to x is negative 2. The partial derivative with respect to y is negative 5. In my vector field, the f component is x, the g component is y, the h component is z. So according to that formula I just put on the other slide, we're going to take the double integral over a region of negative f times the partial derivative of z with respect to x plus, well, I'm doing two minuses, right? So here, let's write it out first and then we'll simplify. So I'm going to do minus y times the partial z with respect to y plus h, which is just z. So I'm taking the double integral over some region of negative 2x plus 5y plus z integrated with respect to area. So I've got two options here. One is to iterate my integral. What does this region look like if z is equal to 0? So if z is equal to 0, then I end up with 2x equals 10 minus 5y, or x equals 5 minus 5 half y. So the x values are going from 0 to 5 minus 5 halves y. Where are the y values going? Well, if I try to plot a couple of points here, if I put a 0 in for y, x is 5. If I put a 0 in for x, then y ends up being 2. So I'm looking at this line over here. So if the x's are going from 0 to 5 minus 5 halves y, right, that's where the x's are going, then where are the y's going? They're just going from 0 to 2. And so I could set up my double integral. X's go from 0 to 2. I'm sorry, y's go from 0 to 2. X's go from 0 to 5 minus 5 halves y for the function right here. Negative 2x plus 5y plus z dx dy. Right, when I go to integrate the first piece with respect to x, before I do that, I should go in here and substitute the function for z. So I get negative 2x plus 5y. What was I originally told z was? Z was 10 minus 2x minus 5y. And all of a sudden, this just becomes the double integral of 10 dx dy. All right, so I get 10x evaluated at 5 minus 5 halves y and at 0. When I do that, I get 10 times 5 minus 5 halves y gives me 50 minus 25y. And now I'm going to integrate that from 0 to 2 with respect to y. So I get 50y minus 25y squared over 2. 50 times 2 is 100. 25 times 4 is 100 also, but 100 halves is 50. That gives me 50. Now, what if I had done that a little bit differently? So I had come back and not worried about limits of integration at this step here, and had come all the way down to where I did negative 2x plus 5y plus z, which we said was 10 minus 2x minus 5y. And I didn't bother figuring out limits of integration. I just said whatever comes out, I'm going to integrate that over the area. And you would have ended up with a double integral of 10 with respect to the area. Question is, what's the area? Well, look at this picture that I drew up here. I got myself a right triangle that's got a base of 5 and a height of 2. So isn't the area of that triangle just 1/2 times 2 times 5? Area is 5. So I could have come down here, and once I got that 10, just said 10 times the area that's 5, 50. Same answer with a lot less work. So you can do that. If you can figure out the area of the base, then you can take that constant on the inside and multiply it by the area of the base, and you'll come up with the equivalent value for that double integral. All right. That's the end of surface integrals.